We thought we understood our neighborhood, the solar system. We mapped it, tracked what moved, and agreed on one thing, that anything passing through belonged here. Objects don't just wander in from elsewhere, so when something did, we wrote it off as pure coincidence. Until it happened again, and again. And suddenly a 50-year assumption collapsed. The discovery that changed space science. First, let's define what is an interstellar object, as it's thrown around next to a blurry telescope image with aliens, and then gravity gets ignored. An interstellar object is a natural chunk of material, ice, rock, dust, sometimes all three, that did not form in our solar system and more importantly is not gravitationally bound to the sun. That last part is the entire ballgame. In orbital mechanics, being bound means the sun can keep you on a closed path like an ellipse. Not bound means you're on an open path, a hyperbolic orbit. You come in fast, the sun bends your trajectory a bit, and you keep going because you still have speed left over when you're done. Astronomers actually calculate that leftover speed. It's called hyperbolic excess velocity. If that value is meaningfully above zero, you're not a local object. You're passing through from somewhere else. For decades, this kind of object was treated as basically mythical. The intuition felt reasonable at the time. Stars are far apart. Interstellar space is enormous. Our solar system is small. So the idea of random debris threading the needle and passing close enough for us to notice sounded like a once-in-a-lifetime coincidence. There will be a fire star tonight. It comes once only 1,000 years. When the fire star crosses the sky, we begin the ritual. Tell me when it passes. Do not look away. Is water wet? No, water makes things wet. Then why does water feel wet? Shh, I think we missed something. You missed the fact that this is wet. The star came directly to the pot. It is a miracle. We built an entire mental model around that assumption, and then the assumption was broken 3 times under 10 years. First came one Oumuamua in 2017, discovered by Pan-STARRS. Then 2I Borisov in 2019, an unmistakably comet-like interstellar visitor. Then, in July 2025, 3I Atlas, found by the Atlas Survey System. NASA didn't overthink the name. Third interstellar object discovered by Atlas. Simple, clean, mildly humiliating for the rare hypothesis. And here's the important part. This doesn't mean the galaxy suddenly got busier. It means our detection got better. From basic planet formation physics, interstellar objects aren't some optional side quest the universe occasionally unlocks. They're baked into the process. When star systems form, planets don't grow politely. They grow by throwing their weight around. As they get bigger, they gravitationally shove smaller bodies all over the place. I hate you. I really hate you. You especially. Okay, you can stay. This one's for you, Big Bang. Or was it a supernova? Whatever. Some of that debris gets stuck in distant parking lots. A lot of it gets absolutely punted. Now throw in the fact that many stars are born in crowded clusters where close flybys are normal and suddenly ejection isn't rare at all. It's routine. Gravity isn't sentimental. It keeps what it can hang on to. Everything else gets launched into deep space at whatever speed the last bad interaction handed it. So there is no surprise that the galaxy is full of wandering junk. The mistake wasn't thinking interstellar space is big. The mistake was assuming that hard to detect meant rare in reality. Detection is the bottleneck. These objects are small, usually dim, moving fast, and they don't stick around. Historically, we simply weren't scanning the entire sky frequently or deeply enough, and our software wasn't optimized to reliably link fast movers before they vanished. When surveys improved, the objects didn't suddenly appear. They stopped slipping through the cracks. Atlas is part of a planetary defense network designed to repeatedly scan large areas of sky automatically every clear night. When systems like that are running continuously, the solar system stops looking empty and starts looking busy. And this is only the beginning. The Vera C. Rubin Observatory's legacy survey of space and time is designed to do exactly what older surveys couldn't. Wide, deep, repeated scans that make it extremely hard for fast, faint interstellar visitors to hide. When 3I Atlas was confirmed as interstellar, a lot of people were primed for another Oumuamua situation. That first object did real psychological damage to the field. It didn't look like a normal comet, showed no obvious tail, yet experienced non-gravitational acceleration, meaning its motion couldn't be explained by gravity alone. Normally that kind of acceleration comes from outgassing, where jets of vapor act like tiny thrusters, but Oumuamua didn't make that easy to confirm. The data was sparse, the object faded fast, and the result was years of debate. Then 2I Borisov showed up and reset expectations in the opposite direction. Its chemistry could be measured using standard cometary techniques, still interstellar, still important, but suddenly familiar. It behaved like something we already understood. Then 3i Atlas completes that pattern in the most anticlimactic way possible. It behaves like a normal active comet. 3i Atlas isn't inert. It's an active comet, which means it's shedding material as it approaches the sun. When sunlight heats a surface, frozen gases in the nucleus sublimate. They go directly from solid to gas and escape into space, dragging dust with them. That creates a surrounding cloud called a coma, and that coma is the reason this object is so valuable. It's not hiding its composition, it's leaking it. Gas molecules don't glow randomly. When they absorb sunlight, they re-emit light at specific wavelengths tied to their atomic and molecular structure. By spreading that light into a spectrum, a technique called spectroscopy, astronomers can identify which molecules are present and estimate how much of each is being produced. This is how a faint, fuzzy point of light turns into a chemical inventory. Early observations of 3i Atlas showed exactly what you'd expect from a distant comet. A dust-dominated signal, a reddish spectral slope, and little to no obvious gas emission. That doesn't mean it was inactive, it means the volatile activity hadn't fully turned on yet. As the comet moved closer to the sun, gas production increased, and observers detected CN, a cyanogen radical commonly seen in cometary comae. More importantly, they didn't just detect it once, they measured a production rate consistent with known solar system comets. Low, but entirely normal. What really locked this in was multi-wavelength data. Observations from NASA's SphereX mission indicated that the coma of 3i Atlas is rich in carbon dioxide, with water ice present in the nucleus. That combination matters. Water ice dominates activity closer to the sun, but CO2 sublimates at lower temperatures, allowing a comet to become active farther out. Seeing CO2-driven activity tells us about how the comet's ices are layered, how insulated the nucleus is, and what thermal conditions it experienced before ever entering our solar system. That's not just chemistry, that's formation history. And because the universe never uses just one diagnostic when it can use 5, 3i Atlas was also observed in X-rays. This doesn't mean the comet itself is emitting X-rays. What's happening is charge exchange. Highly charged ions in the solar wind collide with neutral gas in the coma, steal electrons, and emit X-ray photons. Observations by ESA's XMM, Newton, and Japan's XRISM detected this interaction, confirming the presence of common elements like carbon, nitrogen, and oxygen in the escaping gas. This plasma physics gives scientists yet another handle on the comet's composition and environment. When you step back, the importance becomes obvious. These molecules did not condense around our sun. They formed in a completely different protoplanetary disk, orbiting another star under different temperatures, pressures, and radiation conditions. And instead of speculating about that system from light years away, we're analyzing its leftover building material directly as it vents into space. What 3i Atlas really does is force planetary science to stop thinking locally. Once interstellar objects stop being one-off flukes and start showing up as a detectable population, they become evidence instead of anecdotes. Their speeds tell us how violently other star systems eject material. Their sizes tell us how efficiently those systems build and lose small bodies. Their activity and chemistry tell us where that material formed relative to its star. None of that requires new physics, just enough detections to stop guessing. Instead of inferring how planetary systems work by staring at our own and hoping it's typical, we can now compare systems using their escaped debris as physical samples. 3i Atlas doesn't rewrite the rules of planet formation. It quietly proves that the process has always been larger than one star system, and that we finally have the tools to see it. And that's all for today. Thanks for watching.